Hello everyone. Welcome to Algebra 2 Notes 2.1, Relations and Functions. Chapter 2, as we go through it, you'll come to realize that it is very much like Chapter 1 and that it's a review of many of the Algebra 2, of many of the Algebra 1 concepts that you may have already learned, but we'll just go into a little bit more depth as we jump through them. So let's jump right into them. Again, Chapter 2.1 is just relation and functions. Um, First thing we would need to do is, what is a relation? Well, that's just a set of ordered pairs. This can be a huge number of ordered pairs, or it could just be um, a single ordered pair. So 3, 2, 5, 7. This is a relation. And we could keep on going and just have hundreds of these sets of ordered pairs. And it would still be a relation. We can get rid of everything but just one, and that would still be a relation, a very short one, but still still a still a relation nonetheless. To go into a little bit more depth, to zoom in on what this ordered pair really is, we'll look at domain. So domain is the set of all the first coordinates. The x coordinates in almost every case that you'll see. The domain is the independent, it's the input. It's what we plug in to this machine that we call a function, this number crunching machine that we call a function, and that's it. That's all the domain is. It's everything that you can put into this function or relation in this case. The range, what is the range? Well, that's what the machine is going to spit out. It's the second coordinate. It is the y coordinate. It's the dependent. It is the output. This is dependent on what we put into the machine, this number machine. So if we put in a 1 and we get a 2, if we put in a 4, we might get a 5. That would just be a, adding 1 function. But that's you can't get to the range without first putting something into it. So with no domain, you would have no range. You can have a very short domain and have a very large range. But we'll get through that as we jump through more. So looking into it a little bit even finer and tightening the definition a little bit more, we're looking at functions. Function is a relation, so again, it's just another set of ordered pairs, but it is a relation where each input is paired with exactly one output. That does not mean that we can't get to the same place using different inputs. A good example of that, just to put a picture to it, would be f of x equals x squared. That, I'm sure many of you are familiar with, is a graph that looks like this. Say we're looking at the output 4. We have two different ways we can get there. We can plug in 2. 2 squared would give us 4. We could also plug in negative 2, and that would give us 4. But this one input, this negative 2, will never give us anything else. It's always going to jump to 4. It's not going to go to anything else. If we had a function that looked like this, and there are functions, or I guess they're not functions technically, but there are relations that look something like this, this would not be a function. Because if we plug in, say, negative 2, if this was just an exact reflection, we could get 4 or negative 4. So that would not be a function. And we'll zoom in on that even more as we go through further. So, but that would be a function where each input, every number that we put in, is only ever going to give us one result. What is a one-to-one function? This would be where each element in the domain, so every input, is paired with only one element in the range. This means that this function right here, f of x squared, would not be a one-to-one function because we can get to the same output with different inputs. A one-to-one function does not have that. Every single input is paired with exactly one output, and every one output is paired with exactly one input. You can't get to the same output with two different inputs. That would be a one-to-one function. Let's come up with a few more tactile examples. We'll kind of see what we come up with here. I'm just going to pick some random numbers. I'll probably have you guys throw out some numbers to me in class, but I'm just going to pick some random points here. That's probably plenty. And let's give these some numbers. So this first one here would be over 2 and up 1. That would be negative 2x, positive 1y. This one here would be negative 1, negative 1. This one here would be 0, negative 1. This one here would be 1 up 3, so that would be 1, comma 3. This would be 3, comma 3. And this one right here, let's see, that's over 2, 1, 2, 3, 4, 5, up. So that would be 2, comma 5. This is a relation. Just a random set of ordered pairs, but that is definitely a relation, and we'll look into whether or not that's a function. Some of you guys might be jumping to that, but let's start defining domain and range first. First off, though, the relation is really exactly what we wrote in, so we just need to copy these. So negative 2, 1. We've got negative 1, 1, or negative 1, negative 1. Let's see, 0, negative 1. 1, 3, and 3, 3. And then we've also got 2, 5. These don't need to be in any specific order. Usually you do like to go in sequential order from domain to domain. The inputs, I skipped it around a little bit right here, but that's not a big deal. This is still a relation. They do not need to be in any specific order, so don't worry about that. Now, what about the domain? What are our different inputs here? Well, really, we can just take the first number of all of these. And as we went through, you may have noticed all of them are unique. And I kind of did that on purpose. You'll maybe see why. So we've got negative 2, negative 1, 0, 1, 1, 2, and 3. Terrible at drawing these little things. There we go. A little bit better. Now, what about the range? What are different outputs that we can get? There's really only 4. If we kind of just go up as we're going, well, there's a negative 1, there's a 1, there's a 3, and there's a 5. And that's our range, negative 1, 1, 3, 5. Negative 1, 1, 3, and 5. Of course, separate them with commas. So now our next question, is this a function? Well, every single one of our domain, every element in our domain is paired with one element in the range. Even though we might be able to get to the same element in the range through different elements in the domain, we're still looking at a function here. Let's see. So yes, we are looking at a function. Let's scroll down. And this is actually going to pair in. I'll pan back up just a little bit so we can do the test on our own function up here, or our own relation. So if any vertical line intersects the graph once or less, then the graph is a function. So you may have a restricted domain in that your graph only, let's see, come up with one right now. This is a function, but there's no way to get any type of negative x. There's no negative input. You can draw a negative line here and not intersect at all, and it would still be considered a function. But if it only intersects once every single time as you're going down, then that would also be considered a function. So let's check that on our grid that we did right up here. So if we draw a line straight down through, yeah, that only intersected one. That intersected once, 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 once. So our set of ordered pairs right here, our relation, definitely passes the vertical line test. So I would say yes, it is definitely a function. Let's see. Let's graph the relation y equals 2x minus 1. Really kind of what we're putting in here is going to be the x, so I'll plug in some values for x here. Negative 2, negative 1, 0, 1, and 2. That'll keep us kind of centered right around there. Usually works out pretty well for us. Let's see, negative 2 times 2 is negative 4, minus 1, that'd be negative 5. then we can just kind of add 2. I'm using a little trick of slope here, so I don't need to crunch the numbers every time, and we'll go over that here in a few lessons. But you can check my work. You'll find that it should match up. At least I certainly hope it does. And now we can graph these out. I usually start on 0 just to give myself a nice easy count. Let's see, -1 would be -3, -2 would be -5, and 1 would be 1, and 2, 3. So really what we're getting here is just a straight line. And now we would need to write out the domain. Now, I could just start writing out, well, we plugged in, we'll go -2, we'll go -1, 0, 1, 2. But then you realize you're going to have to keep on counting, and you're going to keep on counting forever. And then you might even zoom in between the 4 and the 5, for example, we're going to realize, well, we could do, let's go 4.1 and 4.2 and 4.3, and it becomes very tedious, of course. You'll realize very, very quick. So what I'm going to do, instead of writing out every number that ever has existed and ever will exist, as far as the real number spectrum goes, is just write that out. All real numbers. Not mumbers, numbers. And that perfectly works. The domain is all real numbers. There's no restriction. There's no number that can't go into our input, our domain, for any reason. And by that same coin, we can get any real number that we want. It might be an odd number if it's a fraction or something like that, but we can still get any number, all real numbers, in the range as well. Because that's shooting up to infinity here, and it's shooting off down to -infinity here. Let's jump to another one, and I'll give you a spoiler. This one is not going to be a function, and you'll see why here in a sec. The first thing to realize is that the x is over here, the y is over here. We can try plugging in x's first, but it's going to make a little bit more sense to plug in the y, and then we'll get our x's after that. So we'll jump through that first. So same thing, I'll plug in -2, -1, 0, 1, and 2. And I'll start at 0. For this one, that'll just make it kind of easy. We'll go -2 here. This will be -1. That will be 2. That'll be not -2, -1. And that'll be 2. We can graph this out. So 0 on the y-axis would be -2. So don't want to get these flipped around. I almost did that. It's going to kind of look like a parabola just turned on its side. Really, that's exactly what this is. Now, even though we were plugging in y's first, even though we were plugging in the y's here, that does not make that the domain. The domain is always x. If we're looking at functions like this, the domain is always, always, always going to be x. So what is our domain here? Well, we realize that nothing exists to the left, or nothing is less than -2. So we can write this, the easiest way to write this would be any real number, and we'll come up with better notation for this later as we continue on through math. But for now, we'll just write it all out. Any real number that is greater than or equal to -2. It can be equal to. We can see that here. If we plug in 0, we would get -2. But then once we add anything more or less than 0 as far as the range is concerned, we're going to start going positive again. So it's any real number that is greater than or equal to 2. What about the range? Is there any restriction as to what we can do? It definitely gets really, really flat over here, but it's always increasing just a little bit. We can get to any number. It might take a astronomically huge y to get there, but we can definitely get to, or I'm sorry, it might take an astronomically large x to get there, but we can. So that's any real number here. There's no real restriction for the range on this function. I'm sorry, not a function on this relation. And how do we know that it's not a function? Well, pretty easily. It does not pass the vertical line test. We have an intersection here and an intersection here. So it doesn't pass the line test, or the vertical line test. Any vertical line, even just one, would show us, if it intersects twice, that we have one element in the domain. In this case, we can pick -1. That can match up to -1, and it can also match up with +1. So this is not a function. Fails vertical line test. I suppose I asked up here, how do we know that this one is a function? Well, it does pass the vertical line test. So yeah, passes vertical line test. And that's everything. If you guys have any questions on this lesson, please see us in class. We're more than happy to help you out, and we'll see you guys there.